Welcome back, everyone. So I wanted to record a quick video about Chapter 4.3, or Section 4.3, because I feel like there needs to be some context or some conversation behind the decisions that we're about to make in how we understand information, okay? And so in Chapter 4, when things get confusing, I challenge you to remember that all we're doing here is we're thinking about taking information and reorganizing it in a way that makes the problem actually simpler for us. Now, the process to getting to simpler stinks, but eventually it will make the problem actually simpler for us. So we're going to be considering a lot of situations where we have now a number of bodies, right? So chapters 1, 2, and 3, we were concerned about looking at one object and trying to study that one object as it existed in some minimum of a potential energy, right? Which convinced us that we were able to describe that object near equilibrium. Now I'm thinking about having a system. So I have more than one object, right? And that system that I'm looking at is still going to have some sense of equilibrium. So the one that I go to a lot are, imagine I have a lot of pendula, and the masses on the end of those pendula are connected by springs. Now, if I walk into a room and I see this apparatus, I see them all hanging there happy, I see a place of equilibrium. I also see a lot of conservative forces. And so I say to myself, there is an equilibrium here, therefore maybe there's a near equilibrium behavior. And as we've been practicing in the first two sections of Chapter 4, I now know how to write down the equations of motion, right? I know how to balance all of the forces for each of these bobs, right? I do this thing where, I say x1 is going to be defined as my distance away from equilibrium, x2, so on and so forth. And then I write down the equations of motion for each one of my bobs, right? And I get something that starts to, it's something I can calculate, and it's something that gives me a little bit of hope, right? There are a lot of linear terms here. But decidedly, what I end up with when I write down these expressions are equations that are linear, yes, but they are definitely not the shoe, right? In order to have the shoe, I need just one thing, right? x1 being proportional to minus x1, right? And I don't have that here because I see that x1 is coupled to x2 and x2 is coupled to x1 and x3. All of these, it's really a system now, right? And so the way that I've written it down here, the way that I've chosen to express the position of all of these bobs, really explicitly is not the shoe. Right? And that's something to keep in mind that as I've written it like this, it's not shoey, just linear. However, the fact that I got this equation was really a choice, right? And the choice that we made was one that made sense in chapters 1 to 3, where I was looking at x1, for example, as the piece of information that told me that I was near equilibrium. After all, the plot of the potential energy showed an equilibrium point at some value of x. The problem gets a lot more complicated when I have more than one body, and you'll notice that we're not drawing pictures of potential energies here because once I have a lot of bodies, it's really hard to think about how to draw those potential energies because there's a dimension for every extra body that I add to one of those diagrams. And so it's clear now that as I look at x1, x2, x3, x4, that the choice of representing my information of the problem as where is x1, where is x2, where is x3, where is x4 is not going to lead us to the shoe. But that was a choice that I said x1 is independent of x2, right? I tried to study those two things separately. But the question for us now is there a way for me to come up with a new set of variables that turn out to be independent? Right? Like, can I take the information that I have, and the information again is, where is x1, where is x2, where is x3? Could I recombine that information in such a way that I get something that actually looks a little bit simpler? And the answer is, of course I can, right? We did this in section 4.1, right? When I looked at the center of mass coordinates, right? there it seemed a little magical, right? I came up with this coordinate transformation, and I found out that I can come up with two new variables, two new positions, right, that are independent of each other. But it took some very specific knowledge of the problem. And now I want to see, is there a way that we can get those definitions? Is there a way that we can define those coordinates without knowing too much information beforehand? So I'm going to start a little bit simple here, okay? And trust me, you're going to like that I started simple, and then I think I'll say something at the end of this video that you'll like even more. But I'm going to start with just two pendula connected by one spring. And I'm starting with this because it's something that we saw in class, right? We saw it on a whiteboard, and we know how to write down the equations of motion for these two bobs, right? X1 has two forces acting on it. It has the restoring force from the pendulum, and then it also has a spring force, because as X2 minus X1 gets bigger, that's going to pull Bob 1. If X2 minus X1 gets bigger, that is, if the spring gets larger, it's going to pull Bob 1 to the right, because it's going to want to get smaller. And so there are two different forces acting on X1. If I go down to X2, well, again, I have a pendulum that's going to pull X2 back to equilibrium, and then I also have a force on X2. If X2 minus X1 gets bigger, then it's going to pull Bob X2 to the right. And of course, as I say that, I note that I've made a tiny little error here, so let me just fix that. That's a minus sign, right? As X2 minus X1 gets bigger, if the spring gets elongated, then X2 is going to be pulled to the left. And what I can do, and let me neaten this up so that everybody is happy, right? What I can do then is I can rearrange this information, and again, this is something that we've had some practice with in class, to write it down in a way that really looks like a system of linear equations. And I've corrected the sign error as I came down here. On the left-hand side, I have x1 double dot and x2 double dot, and I've sort of written it as a grid, where I have what is it times x1 plus what is it times x2, and then the same structure on the bottom. And I really like to do this just because I visualize this as having a left-hand side, and then having something that looks like a matrix on the right-hand side, where I have things that depend on x2 and things that depend on x1, And so in my mind, I've really taken this problem and I've started to decompose it into something that maybe reminds us a little bit of linear algebra if you've taken linear algebra, but it surely makes me think that I'm organizing the problem in such a way that I know, well, how does x1 change based on x1? How does x1 change based on x2, etc. Okay? And this structure then helps me to write down this entire system of equations, Now, note the language that we're using here. We have a system of bobs, where we found out that x1, x2, x3 are not independent of each other. So how do we unindependent them? We have to collect them into some new structure. And that new structure is matrix algebra, Because if I write down this vector x1, x2, then I can take all of that information from my system of equations, and I can reorganize that information of the system of equations into a matrix. And now, when I write it like this, now this is something that starts to feel pretty shooey, Now note, I've taken an overall minus sign out of this. So in fact, the matrix that I'm defining as gamma is not the one that I see here. It has an additional minus sign. So it's G over L plus K over M along the diagonals. And then on the off diagonals, it's minus K over M. But that's okay, And the minus sign there is purely to make it look as shooey as possible. So that way we can think about it as something that's truly shooey. Okay? And so this, and again, it feels shooey. It's not shooey, of course, or it's not the shoe yet, because this is still a system of equations, That gamma is not a constant, It's a matrix. And in order to be the shoe, that thing has to be I have to have something proportional to minus itself, right? And right now, that's not proportional because that thing is a matrix and not a constant. However, it begs the question now. My matrix that I have in that expression, x, is my information, x1, x2, x3, blah, blah, blah. But my goal is to rearrange that information in such a way that maybe I can get the shoe out, right? Maybe I can rearrange it so that I actually have the shoe appear in different places. And so the question that we ask, and at this point it really still is a question, is whether I can take that equation and say, well, maybe there exist some vectors, some set of vectors, which I'm going to call v sub I, so that just indexes them. And for that set of vectors v sub I, is it possible to take my equation and write it as v sub I is equal to minus omega squared v sub I, and that is the shoe, because in this case, those omega squareds are just constants. They're not matrices. And so the question is, how do we find those vectors, right? And in order for this to be satisfied, of course, that means that the gamma v sub I has to equal omega squared times v sub I, right? That's going to take that right-hand side of my previous equation, and it's going to really turn it into the shoe. Okay, and so now, again, let's track the progress, right? We took our information of each of our bobs, we rearranged it as a system of linear equations, we wrote that in matrix form, and now we're asking, is there a transformation that will allow me to find vectors such that that matrix equation looks like the shoe, right? Or is the shoe, not just looks like the shoe. And if you've taken linear algebra, or not, it doesn't matter, because we're going to do it together slowly anyway. This is what's called an eigenvalue problem, okay? And that is we're trying to find out what the eigenvalues are, those are the constants, and what the eigenvectors are, those are the vectors that'll come out of this. So how do we do that? Well, okay, so first I have to multiply the right-hand side by the 1 matrix, right? This 1 here is the identity matrix. So for us, that's 1, 1 along the diagonals. Then I can subtract from both sides, and I can get a matrix equation that's equal to 0. This is important because now I have something equal to 0, and if I want to do more to it, if I want to get any more information out of it, I have more tools if it's equal to 0, and so I can say, well, if the determinant of this left-hand side is equal to 0, well, the vector can't be 0, right? Because those are the things that I hope to solve for. Therefore, the determinant of the thing in parentheses must end up being 0. And so by saying the determinant of gamma minus omega squared times the identity is equal to 0 is going to ask the question, are there values of omega squared for which this can be solved? Okay. And this looks complicated, and it is complicated. It gets a little bit easier when I write it out in the example, which I'm going to do in a second. But yeah. Okay, so let's do it. Okay, so this is that gamma that I had from a couple slides ago. I'm going to now subtract omega squared times the identity from it, and I get this matrix on the right-hand side of the middle of the slide. And that looks terrible, right? I mean, there are 3 terms along the diagonal, right? So this is something that even for the simplest possible case, right, just 2 bodies and just 1 spring, that I've already gotten a matrix that's starting to make me feel a little bit anxious. Well, now that I have that matrix, I have to take the determinant of it, which is the multiplication of the 2 diagonal things minus the multiplication of the off diagonal things, and I get this equation down here at the bottom, which I hope to be able to set equal to 0 and solve. This thing is called the characteristic equation, and it's the piece that I was hoping to get to, right? So this is kind of when the problem gets maximally conceptually complicated, is when I get to the characteristic equation and I ask myself, are there solutions to this for omega squared, right? Because it's omega squared that's actually the constants in that equation that I want to know. And you look at this and you say, oh gosh, okay, well, it's algebra. I took algebra. And so you take that equation and you expand it all out, and you notice that, okay, minus k squared over m squared, yeah, that cancels that, right? And I'm left with these things, and now I can group them in terms of omegas, right? This is the thing that I want to do when I think about how to solve an equation like this for omega. And then you take a deep breath and you're like, can I solve this for omega squared? And you're like, oh, shoot, it's a quadratic equation, right, for omega squared. All right, so write it as a quadratic equation, the opposite of b, plus or minus the square root of b squared minus 4ac. Okay, this looks terrible, but let's keep algebraing. At least there's a 2 or something that I can cancel in each term. Note I'm going through this a little bit fast, but it's algebra. Go ahead, pause me and go through it yourself. Please do, so that you can convince yourself that I'm not making any mistakes. Now, inside that square root, I can FOIL everything out, and actually, it's kind of cool, right? Now suddenly all of these things are canceling with each other, and I'm left with an actual solution for what omega squared can be, right? So omega squared is g over L plus k over m plus or minus k over m, which now says, okay, there are 2 solutions for omega, right? There are 2 possible omega squareds that I can get out of this problem. That's not totally surprising because I started with 2 bodies, right? And so sort of when I think back to it, it's like, oh, well, before I had 2 pieces of information. Where is x1? Where is x2? No matter how I rearrange 2 pieces of information, I'm probably going to end up with 2 pieces of information. And this sort of reinforces that. And those 2 pieces of information have an omega associated with them. And those omega squareds are given by the constants of the things in the problem, right? G over L and G over L plus 2k over m. So I have found, in the parlance of our times, I found the eigenvalues, right? I know that I can write this as shoes, but I still haven't really solved them because I don't know how to rearrange the information yet. And so even though I found the eigenvalues, now I have to go back and find the eigenvectors. And this is really brute forcey, right? So for each of the eigenvalues, I have to go in and I have to find out what is that eigenvector. And for that, I go back to the definition, right? That gamma, right? Gamma times the vector is going to equal omega squared times, and this is just v1, times v1. And since I have no idea what v1 is, the general thing to do is to just guess a general form of v1. So here I'm going to use AB, plug that in, and try to solve it for equations, right? So now I'm doing the matrix multiplication out, and I get this expression here that comes from the top row, right? So g over L plus k over m times A minus b times k over m is equal to omega 1 squared times A. Okay. But of course I know what omega 1 squared is, right? Omega 1 squared is g over L. So that allows me to do a little bit of simplification. And again, and this happens so often in these eigenvalue problems, after all of this algebra, I get something simple like A equals B. And so what this tells me is that in order to think about this omega 1 equals square root g over L, I know that the x1 and x2, right, which are the top and bottom entries in this vector, must be equal to each other. Right? They both are equal to A. Now, eigenvectors, for those of you who've taken linear algebra, are not unique, right? There's always an overall constant in an eigenvector, and that's what we found here. I can't do better than this, right? Because I can multiply vectors by a constant, and they just scale out. So we have a convention now that we so-called normalize eigenvectors, which means that if I take the dot product of v1 with itself, that's going to equal 1. And so if I do that here, that means a squared plus a squared is equal to 1, which means a is equal to 1 over the square root of 2. Okay? And this is just convention. It's just a way of thinking about the eigenvalues, or thinking about the eigenvectors in a way that makes some math a little bit easier. But once I normalize it, now I can really visualize what this means, right? So V1 is telling me that if I change x1, I'm changing x2 by exactly the same amount. And so visually what that means is that if x1 gets bigger by a certain amount, x2 gets bigger by a certain amount. If they go back, if they go to the left by the same amount, they go left. Well, now the two bobs are just oscillating, where the spring in between them is not changing in length, right? X1 gets bigger, X2 gets bigger. They get smaller together, they get bigger together. They get smaller together, they get bigger together. And of course, if I now visualize that, the only thing that matters in this system is the pendulum, right? And that's why the omega associated with this is just the omega associated with a pendulum, because they're swinging back and forth, right? And that turns out to be the thing that's independent, right? That turns out to be the way to reorganize this information. That way you end up with a shoe. And of course, if the whole system is going left to right to left to right, that is oscillating. That's obeying simple harmonic motion. That is what we call a mode of the system. I'm not going to do all the algebra associated with the other one because it's harder, and all I end up with is a -1. And so now V2 is when the two bobs go out together and in together and out together and in together and out together and in together. This is this mode here, when it goes out, what's being pulled back? Well, there's both pendulum forces and the spring force now, and that's why the omega squared for this combines both G over L's and K over M's, and it's going to tell us that frequency is just a little bit bigger than the frequency associated with the first mode. But I can now take any behavior of this system, right, and instead of decomposing that behavior into where is x1 and where is x2, I need to think about that behavior as how much of it is oscillating left to right, and how much of it is oscillating out and in. Because left to right is now independent of out and in. Right? So I've rearranged the information by finding these eigenvectors, and now not only do I know how the information should be organized, I also know the frequency with which those modes actually oscillate. Okay? And so when you see two bobs, two pendula connected by a spring, rather than thinking about it as where is bob 1 and where is bob 2, we think about it as how much goes left and right and how much goes in and out. And that set of information is a lot easier to work with. Okay, we're going to do lots of problems with this, and my promise to you is that although you will have to do some 2x2 systems, or you'll have to do some two body systems by hand, you will never have to find the eigenvalues and eigenvectors of anything bigger than that by hand. For that, we are going to use Mathematica.